everyone, this is Rankine, real versus ideal. So we have alluded to this video in a couple different spots, talking about why it's maybe not the best assumption that a process doesn't have friction and thus the entropy doesn't change. Because remember, the entropy always increases when temperature is increased or Q is added and friction is present. So let's look a little bit about how that actually affects our thermodynamic properties. I was struggling with the word. How it affects our thermodynamic properties if we make the assumption that we're looking more at a realistic versus an idealized situation. So if we have a temperature entropy diagram here with a vapor dome, we have this top line, which is the pressure of the boiler, and the lower line, which is the pressure of the condenser. And let's walk through the process of, we start somewhere up here, maybe in the superheated vapor region. And what we are going to do from there normally is that we draw a line straight down and assume that no friction was present. Entropy is staying the same between point 1 and point 2, which, not a great assumption. So what does it look like if we actually do consider that there is friction present? So if we do, it actually just moves itself a little bit to this side, which again, thinking about the shape and what this would look like if I wasn't the one drawing it, this might actually still be in the wet vapor zone, but I'm not a great artist and didn't make that happen. But basically we have this 2 ideal, which is this one, and then we have 2 real, which means that our entropy on this bottom condenser line of point 2 has shifted just a little bit to the right. So it's looking a little angled from that point 1 instead of straight down, assuming the entropy stays the same. From 1 to 2 real, we are assuming that the entropy is increasing because we are decreasing the pressure. It is going through a turbine. There's going to be friction present, and so there is going to be this realistic. That means that in a turbine, we're getting a little less energy than we would like to, than we would ideally like to have, because friction is present. So across a condenser, as we come this way, so we're working down this direction, a condenser isn't affected by friction in the same way, and our entropy is just decreasing here as we remove Q over to point 3. But then we come to the same process here of thinking about a pump. And before, we had made the assumption that we were just going straight up to point 4, and let's call this 4 ideal. And that, again, bad assumption, because in a pump, there is going to be friction present. So we are actually going to go a little bit to the right here and get point 4 real, which assumes that your entropy isn't going to stay the same because friction is present, so it's going to increase a little. And remember that to the right on this is the direction that entropy increases. So then you're going to work your way up this way on this real cycle and across the boiler, where again the entropy is increasing because we're putting in Q, so we don't need a real versus ideal there. We're already assuming that Q is transferred in. And so that's what our real cycle is going to look like. So again, in a turbine, that means we're going to get a little less electricity than we would like. In a pump, it means that we're going to have to put a little more energy in than we wanted to pay for because friction is present and there's going to be losses. And that's also going to affect our H values, because you know from the videos finding H, when we went from 1 to 2, we were just assuming that the entropy was staying the same. Well, if we can't do that, how do we find it? So let's go to our equations where this is going to matter. So if we have our efficiency, so let's go, our thermal efficiency of a turbine is the work real over the work ideal. And we know that for our work real in the terms of H, so let's go to H for the work real, which is we're trying to maximize our turbine. So that's going to be H1, where the energy is higher going into the turbine, and you're going to subtract H2. And if it's real, we're going to put the R there. And then that is going to be over, I should put this as turbine. Let's write this specifically as turbine. So remember, this is just for the turbine. We'll talk through what it looks like for the pump. But this is just for the turbine. So H1 minus H2 real over what it was ideally. So this, we have some knowns and unknowns. So H1, we know how to find that. H2 ideal, we also know how to find that because that's where we assume the entropy is the same. We're able to find 2 ideal. And for a turbine, you actually are able to look up this value because manufacturers of turbines will give you curves that tell you if you run at a certain pressure, at a certain flow rate, this is what your efficiency will be. So you'll be given this value. You'll be able to find it. And so the only thing that you don't know is H2R. And the reason we have real over ideal here is that, again, remember for a turbine, what you're really going to get out, the power that you are going to get out, that you're going to be able to sell, is slightly smaller or a lot smaller, depending on our efficiency, than the ideal value. I would like to get a whole bunch of power out, but because of the efficiency, I'm going to get a little less power out. So we will be able to find what the efficiency of the turbine is. So what does that look like in a pump? Well, let's think about in a pump, again, the inefficiencies are going to make me have to pay a little bit more for a bigger pump or a little more electricity to be able to actually get the delivery that I need. So we have the ideal, which is a little bit smaller than the real or actual. So in this case, our ideal is going to be equal to H4 ideal. So that's what's coming out of the pump minus, and out of the pump is more energy than going in, so minus H3 over H4 real, so again, moving a little bit to the right, minus H3. And so because of that, and again here, this is going to be given by pump curves provided by the manufacturer. You can find H4 ideal, you can find H3, and H3 is again on the bottom, so again, your only unknown is H4 real. So you are able to calculate this. And the reason we do this is because you have to account for friction. It gives you a more realistic view of the cycle because friction is present, which means entropy goes up. It's not equal in these processes. So that is your scope of what does it look like real versus ideal in the case of a Rankine cycle.